Welcome to Quiz channel. Today we are looking at TPU vs GPU, one of the most important comparisons in modern AI hardware. We will break down how they differ in purpose, architecture, performance, software support, and practical use cases, and quizzes along the way will test your understanding. Modern AI models, especially deep learning systems and LLMs, need huge amounts of computation. Ordinary CPUs are not enough for this kind of matrix-heavy work, so specialized accelerators became essential. GPUs became the default choice because they handle parallel tasks very well, while TPUs were built by Google specifically to speed up neural network operations. So first let us understand what each one was designed to do. A GPU was originally made for graphics rendering, but its many parallel cores made it perfect for deep learning too. That is why GPUs are now used not only for AI, but also for gaming, visualization, NLP, computer vision, and high-performance computing. A TPU, on the other hand, is purpose-built for tensor and matrix math, which are at the heart of neural networks. In simple words, GPU is more general purpose, while TPU is more specialized for large-scale AI. One big strength of GPUs is flexibility. They work across many environments, whether you are training models in the cloud, running experiments on-prem, or even using consumer hardware. They also have a mature software ecosystem, especially with CUDA, and this gives developers access to many libraries and tools. For teams using PyTorch heavily, GPUs are usually the most natural fit. TPUs are designed to push throughput very high for deep learning jobs, especially when models become extremely large. Google also allows them to scale across TPU pods, which means thousands of chips can work together for distributed training. Their software stack is strongest with TensorFlow, JAX, and XLA-based optimization. So that covers the main purpose difference. GPUs are broad and flexible, while TPUs are focused and highly optimized for neural network workloads. Now that we've covered purpose and positioning, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What best describes the original design purpose of GPUs? The correct answer is graphics rendering and parallel computation. GPUs were first built for graphics, and later their parallel architecture made them useful for AI and many other compute tasks. Question 2. Why are TPUs considered more specialized than GPUs? The correct answer is they are built for tensor and matrix math. TPUs are purpose-built AI accelerators, mainly optimized for the tensor operations used in neural networks. Question 3. Which setup is usually the better fit for heavy PyTorch usage? The correct answer is GPU with CUDA ecosystem. GPUs have broad PyTorch support and a mature CUDA ecosystem, making them a common choice for research and development. TPUs use a design centered around systolic arrays, also called matrix units, which are excellent for repeated matrix multiplications. This is exactly the kind of work deep learning models do all the time. They also support bfloat16, which gives near FP32 accuracy with better speed and efficiency. Features like unified on-chip memory and sparse core make TPUs especially strong for large embeddings and large-scale model training. GPU architecture is different because it is designed for more varied workloads. It uses streaming multiprocessors with thousands of CUDA cores, and modern GPUs also include tensor cores for fast mixed precision matrix operations. Their cache hierarchy helps them adapt to different access patterns, which is useful beyond deep learning. With NVLink and NVSwitch, multiple GPUs can also communicate quickly in larger systems. When we talk about performance, the answer depends on the workload. TPUs are especially strong for large-scale training of transformers and CNNs, and they can deliver very high throughput in distributed settings. They also offer very high memory bandwidth, around 5.2 terabytes per second in some cases, which is excellent for huge LLM workloads. GPUs still perform brilliantly though, especially for mixed precision tasks and lower latency execution on smaller models. Latency is another important factor. For smaller models or situations where fast response time matters, GPUs generally have an advantage. TPUs tend to shine when the workload is batched or distributed across many chips, where their design and interconnects help maintain throughput. Now that we understand the architecture and performance picture, we have a complete view of how these accelerators differ technically. Now that we've covered architecture and performance, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. Which TPU feature is specifically designed for matrix-heavy neural network computation? The correct answer is systolic arrays or MXUs. TPUs use systolic arrays, also called MXUs, to accelerate repeated matrix multiplications efficiently. Question 2. What is a major architectural strength of GPUs for varied workloads? The correct answer is flexible SMS, caches, and tensor cores. GPUs combine streaming multiprocessors, tensor cores, and cache hierarchies to handle many different kinds of tasks. Question 3. Which statement about latency is most accurate? The correct answer is GPUs generally do better on smaller models. The article notes that GPUs usually offer lower latency for smaller models, while TPUs perform strongly for batch and distributed workloads. Software support often decides hardware choice more than raw specifications. TPUs are tightly integrated with Google Cloud and work best with TensorFlow, JAX, and XLA-based optimization. They also benefit from distributed training tools like the Pathways runtime. GPUs, meanwhile, support a very broad ecosystem including PyTorch, TensorFlow, JAX, CUDNN, TensorRT, and Rapids, which makes them easier to adopt in many environments. In practical use, TPUs are a strong choice for training very large transformer models, serving production-scale inference, and running recommender systems with huge embeddings. They are especially attractive when the whole workflow is already on Google Cloud. GPUs are better when you need flexibility, local deployment, or a mix of AI, simulation, and HPC tasks. Researchers also prefer GPUs because they can adapt quickly to changing experiments. Cost and efficiency also depend on what exactly you are running. TPUs can provide better performance per dollar for very large training jobs, and some generations are more energy efficient for inference too. GPUs are easier to find, come with more pricing options, and support a wider range of custom workloads. So that completes the comparison. Choose TPUs for massive TensorFlow or JAX workloads on Google Cloud, and choose GPUs for flexibility, PyTorch, and broader computing needs. Now that we've covered ecosystem and choice, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. Which framework combination is most naturally associated with TPUs? The correct answer is JAX and TensorFlow. TPUs are strongly optimized for JAX and TensorFlow, especially with XLA-based compilation. Question 2. For which scenario are GPUs usually the better choice? The correct answer is maximum flexibility across mixed workloads. GPUs are preferred when teams need flexibility for ML, simulation, HPC, local systems, or custom setups. Question 3. When might TPUs provide the strongest value? The correct answer is very large transformer training jobs. TPUs are designed to deliver strong throughput and good cost efficiency for large-scale deep learning, especially transformer workloads. So now you know how TPUs and GPUs differ in design, speed, ecosystem, and practical value. Hope you also checked your understanding through the quizzes and saw where your hardware knowledge is strong. If you enjoyed this interactive learning format, do like, share, and subscribe to XplaQuiz channel.